Hello, it's your boy, the one and only Sir Patrick of the Department of Biology. Tara, kape tayo. Alam ko yung iba sa inyo, kailangan na talaga magkape para magising na sa katotohanan na hindi niya kayo mahal. Hindi, joke na. But I know some of us really need that caffeine boost, no? Especially some people. They really need a lot of caffeine, a high dose of it, for them to wake up to what the government is doing. But yeah, anyway, ang dami ko ng segue. Welcome to Lecture 6, titled... Ano nga ba title nito? Yeah, The Fundamentals of Phenetics. So, enjoy those coffee and tune in. Fundamentals of Phenetics. So, looking at phonetics, if you look at its root word, you can easily sense that phonetics pertain to phenotype as its root word from it. And, well, that's true, no? Because, well, in phonetics, you always look at the different phenotypes of your organism, the different characters, the different forms of your organism. And phenotype entered the lexicon of your scientific community around 1910 and was based on the German word panotypus, which was also based on the Greek word panein, which means to appear or for appearance or shining, no? And when we talk about phenotype here in phonetics, we pertain to not only the morphological physical appearance of your organism, but also its behavior, its ontology, and we'll also look about the different types of phenotypes that are organism. But mainly, we'll talk about the morphological characteristic of your organism, the things that we can measure right away. Unlike your behavior, which is also a phenotype of your organism, but it is not easily converted into numerical forms kasi. And in phonetics, we'll look more on the different numerical phenotypes of your organism, different measurement morphologically of your organism. Phenotypes are the observable characteristic of the organism, the physical attributes of the organism, whether it has a black eyes, the color of his iris, or brown, green, or yellow, or whatever color it is. So that's phenotype, the observable characteristic or attributes of your organism. And that's what we use in phonetics. We use all those values and incorporate it in the clustering analysis that we do in the creation of the tree that we are making here, okay? Or clusters or groupings that we're doing, okay? So phonetics, in a nutshell, is an attempt to classify organisms based on the overall similarity. Usually, we pin this classification on the morphology of the observable trait of the organism. And the thing about phonetics, the cool thing about it, is that it doesn't involve phylogeny or evolutionary relationship in order for it to make sense of the classification or grouping or clustering in the data. Okay? So that's the cool thing about phonetics. So it is a numerical taxonomy which is concerned mostly on the numerical methods of taxonomic classification. So the fundamental position of phonetics and numerical taxonomy largely rely on the number of the information that is there, no? And if you kind of look at it, have a look at it, you will see that the more the information that you feed the system of clustering or ordination that you're using, the more data that you're feeding into the system, the more natural looking the tree will look like. Okay? So the greater the content of information in the taxa. So if you have so many measurements for the taxa that you are studying, the better, because you will have a much better classification scheme as a resultant, no, of that. So it's actually important to have many characters and different measurements for that certain taxa for your classification to be more of a natural fit. Because that's the thing with numerical taxonomy. It usually needs a lot of these numerical variables or data points to create a certain taxonomic classification. So that's numerical taxonomy. And if you think about it, phonetic techniques uses different various form of clustering and ordination method to create a sophisticated way of classification scheme, no? While also reducing the variation observed in your organism, making it much more manageable for us. And if you remember, phonetics was actually pioneered by Michael Anderson, in which he specifically stressed the importance of the overall similarity and the equal weighing of your characters. So because phonetics and numerical taxonomy is an a priori model in which you of reasoning in which you must put an equal weight on the every character that you are measuring, every measurements that you are recording, even if it's lip tip, lip margin, lip base, lip shapes, all of these characters in the eyes of numerical taxonomy, they are equal in weight. They are all used equally in creating the the taxonomic classification scheme of numerical taxonomy. Because the more characters that you measure, as we have mentioned, in an a priori principle, the more the more data points that you have, no, the wing length, the tail area, the wing area, the wingspan, the hand length, all of this, if you can measure more of it, it could actually be beneficial to create the distinguishing factors between your lineages, between your I mean between your clusters, between your groups, your groupings that you're um, suggesting. No, it's an a priori model as compared to a posteriori from our lecture 2, because it is more akin to the justification of the classification scheme, no, the taxonomic classification scheme by that is independent from your experience itself. It is like a pure reasoning, no, a deduction of the grouping, the clustering, by the means of your different measurements that are equally treated. Okay. So that's numerical taxonomy. You measure every details of the organism of the taxa that you want to study, and you create the classification scheme that you want. So after collecting all the measurements, it's just a simple clustering analysis or ordination tool to have a resultant tree. No, it's an a priori, and thus it gives equality on all the measurements that you have, whether it is the limb measurement or anything. And usually these characters, you can see them in your taxonomic keys in your plant taxonomy. Those are the characters, no, that are being used right there in your taxonomic keys: the length of the leaf, the length of the ovary, how many partitions are there in the ovary, and so on and so forth. All of those things that you can see in your dichotomous keys. So the overall goal of numerical taxonomy and phonetics is to create a sense of overall similarity among your cluster, among your groupings of organism. If it can create this sense of overall similarity from the data points, it can suggest that this particular organism is of the same are of the same genus or of the same family, because they have a sense of certain similarity, a a sense of individual similarities. So that's the thing about numerical taxonomy. It needs to have this data set to create an overall similarity, or on the other hand, it can also distinguish between different species. If it can cluster organism or group organism into one, it could also distinguish if the other organism is different. So just like what I'm showing here, so pareha silang, I mean, kilala nyo ba to? Si yung basketball player na to? And si Sir Geno of the bio. So parehas silang, if the clustering analysis groups them together due to the sameness of their hairline, the similarity in their brow, and their smile, and so on and so forth, all these data points, their height, no? If the ordering analysis or the clustering analysis look at all these data points and figure out that they are of the same group, it will lump them together. It will cluster them together into one group, into one genus, into one family. But say for example, there is a thin man right here. Say there's a person close to them, no? So let's just say this is a very wonderful man with a quite peculiar body shape. Let's just say there's a person like this. And they compare, the clustering analysis also measures different parts of your organism, the height, the limb, all of those characteristics that was measured here too, no? But what it finds out is that these organisms, this group of organisms, are completely dissimilar to this group. So that's what it will do, no? It will create clusters among clusters based on the different data points that you are feeding the system. Okay? It somehow correlates all those different characters equally. They treat all those measurements, no? So all the measurements that you put in the system, what the system will do, the clustering system or the ordination system will do, is that it will look at all those characters and it will make a correlation or a sense of your data, and it will spit out a tree-like clustering of your different organism. So that's the thing about Phenetics. It's pretty cool actually. The modern version of Phenetics is your molecular sequencing, no? I mean the local alignment of different sequences. So that's that. Anyway, what numerical taxonomy will do is it will recognize if there is a distinct taxa in your study. And how do it recognize that there is a distinct taxa? Well, simply by recognizing the different correlation of different characters. Simply by correlation of the different characters that you put into it. That's how these different organisms are being compared. They are weighted on their character, the different characters that they have. So it works more of a tag, no? That's why it's better if you have more data points to refine your tree, to refine your clustering analysis. Because if you have only few characters, say for example, you have only fruit color or flower color, if all those organisms that you are studying have the same flower color, your tree would look like a simple, well, not a tree, no, more like a fork or something. It wouldn't make sense. So in that sense, numerical taxonomy can create a phylogenetic inferences, just an inferences. It can create certain taxonomic groupings, no, based on the correlation of your characters that you're studying. And if you give it enough assumptions about the evolutionary pathways and mechanism, it can really create a very good phylogenetic inferences of your data points, even though it does not really incorporate that in the data. So that's the thing about numerical taxonomy. It can create phylogenetic inferences based on your correlations of your different numerical data. But the thing here is that you need to have, ito yung pinaka-importante dyan, you need to guide your data. You need to guide it to have an evolutionary sense or the different mechanism that could have happened. Because the data cannot distinguish this. The data in itself, the beauty of the data is that it does not do that. No? That's the good thing about numerical taxonomy. It does not involve itself with the previously known processes of evolution. It does not input that in the data. It does not concerns itself with the different evolutionary relationship of organism. What it does is that it looks on the data, on your data itself. So the beauty of it is that, but it also means that the analysis is blind. No, if there is a certain evolutionary pathways and mechanism that is also present in your data that could affect your data, your numerical taxonomy cannot distinguish that. So you need to actually guide it on the different evolutionary pathways and mechanisms that are happening. So taxonomy here is viewed as a more of a mathematical approach, no? An empirical science. It's like a data science actually. And your classification that are based on this numerical taxonomy is purely on the phenetic similarities, morphological similarities, or the similarities in the above mentioned character traits, no? So your classification is purely based on the characters that you're measuring. The classification scheme that you will create is based on the characters that you have measured. That's the beauty of numerical taxonomy. So how do you do phenetic classification? How do you create phenetic studies? So the first thing, as we have mentioned, the first things first you need to do in your phenetic classification, to do a phenetic classification, is one, to collect the raw measurement of the data. So you need to set a certain number of characters. The more, the better. No? You need to create different measurements of your characters. And number two, you need to, of course, well, this is actually the first one, you need to assign your operational taxonomic units, your OTU. When we say operational taxonomic unit, we use this because we are aware of the fact that there is a problem with the word species. No? So instead, we use an operational taxonomic unit. We use OTU. When we say OTU, it's more of a definition from us. No? It's more of a definition of a species for us. Well, not really a species, but more of a group. Unequivalent to the species, but more of a group that we're looking at. That's your operational taxonomic unit. Okay ba yun? When we say operational taxonomic unit, it is a taxonomic group that we, researcher, create to simplify our study, our explanation of which is which. So usually, when we create an OTU, we specify how much degree of variations in the DNA sequences, how much degree of variation in the morphological measurements are there, for us to have a better grasp, a solid and hard grasp of what we are talking about. So that's your OTU. So after defining your OTU, after measuring a lot of variables and data from your organisms, you need to treat your data and measure the correlation coefficient. When we say correlation coefficient, this is the measure of how similar or how dissimilar your organisms are. Your OTUs that you are comparing. No? Hindi na organism, OTUs na yung sinasabi natin to be more precise. No? So essentially, this is a statistical measurement of how similar or dissimilar your OTUs are, your groupings are. And if you look at it here, your data, sometimes before feeding your measurements to the system, to the computer, you need to transform some data in order to remove some redundancy in order to actually create a more, in a sense, to create a more streamlined data. Because sometimes your data have to be normalized. When we say normalize, no, some data kasi is not always, some data is not always numerical, no. Some data are categorical. So sometimes we convert those categorical data into a numerical data for us, no. There are different data types. But the important thing, and the thing that I want you to look at this, is that you need to transform your data to create a normal distribution, a more or less normal distribution of your data set. Because remember, we're dealing with variations on your data, different numbers of measurements. So some data needs to be transformed to reduce redundancy, to normalize them, and to have a value in a common scale, no? A certain bell curve, kumbaga. That's the thing with this, no? You need to do that. And then the last part of your phonetic methodology is simply the agglomerative or the clustering methods, or groupings of your OTUs. This is, of course, the most important part of your study. You need to cluster them. So there are different clustering algorithm. When we say agglomerative, it's just combining or joining together, no? Merging into something, into one tree, or yeah, in the same nature, no? Basta merging into someone, in something. Yeah, conglomerate, the rock, sedimentary rock. No? So essentially, what we're trying to do here is we're creating this clustering, these clusters, no, by different clustering algorithms. And I might speak like a Greek here, but what happens here is that there are different clusters that you could create using this one. And then what it does is it will either create a resultant cluster that includes, that merges your OTUs into one, or it could either create a cluster or a tree that separates them into different clusters. So essentially, this part is just clustering procedure. It's an algorithm based, no? Algorithm lang talaga to. And your clustering diagram here is, your clustering diagram will be converted into a more digestible taxonomic classification scheme, by which, of course, the researcher will figure out which level for each taxonomic rank, no? Identifying the cluster that are distinct and which are similar, and so on and so forth. And here, you need to assign those rank and classifications. So what are the advantages of using numerical taxonomy? The first one is that numerical taxonomy has the power to integrate data from different sources, whether it is morphological data, your physiology, your different chemical affinities, your chemistry, the DNA strand, the sequences, your amino acid sequences, your protein sequences. All of this data can be integrated into the creation of your classification scheme. And with those data, you can do a lot of things actually, and you can create a more accurate classification and descriptions, no, of your organism. You can create a more accurate classification scheme if you have all of those data sources from different fields. That's why you can, no, since you have different data points that you can use, you can more or less create a more robust analysis, no, for example, for the case of your frogs here, no. So if you have different measurements of different data points from different fields of study, you can use all of those studies, all of those data points in your analysis, in your classification scheme, and with that too, you can create a more robust way of proposing new species classification, new genus or new species level. If you have so much data points to use, you can use that as a backup for your classification scheme, no? And this is what I have been talking about, no? This is the, usually it is not, no, it is not flushed, meaning hindi sila pantay-pantay, kung makikita nyo, diba? And we have what we call bootstrap value right here. Okay, and we also have a scale bar, and we also have, that's it, no? So ito na yung practice natin for tree, no? You need to look at this different length of your branches, different, so the length of the branches is, ayan siya, may trait value tayo. So the longer, the more character changes that have happened. And when we're looking at the bootstrap value, we need to have at least 80% or 90% or higher value for us to classify that they are indeed of the same cluster. So these cluster values are okay. Look at this. Okay, it's okay, it's okay, but it's actually not okay since it's only 90 replicates. But for the case of this, it has 100 replication, no? Bootstrap replication, but only one out of those 100 was, so it's just 1% of those 100, only one. It's a very low bootstrap value. Therefore, you can use that as a well, as a basis to classify these two as different from this organism right here. Things like that, no? You need to look at those different things in your tree. So your bootstrap values are actually important in the phylogenetic tree too, because the higher the bootstrap value, the better for the clusters that you have created, to the tree that you have created. If you have a bootstrap value that is below 80%, that's unacceptable, no? That could not support the tree that you are proposing or the branch that you are proposing. It needs to be at least 80% or 90% higher so you can really support the data that you have. So the other advantage of using numerical taxonomy is the automation that it offers us, no? The large portion of the taxonomic process will not be on the burden of on our side, but on the burden of the computer system that we're using. So the large portion is already automated, and since it is automated, the computer can do it for us. We just need to sit back and relax and let the computer do its thing. And thus, it is more accurate and more efficient. And we can take our ass out for a couple of drinks, no? While the system is cranking up the clustering analysis. It's very automated. It's easier. It's a lot easier. Well, the clustering portion, no? And of course, all the data that you have measured can be encoded and converted into numerical forms, and thus we can create a database of these different electronic data or these different data points to create a system, no? More like a catalog or maps, no, of different character points of your organism. So it's easier for documentation process. And the thing about these two is that you can look them up in the web. For example, if you have a database of these different data points or measurements, no, of your organism, you can create a catalog, and you can also, in with that, no, if you have a database of the different characters of your organism, you can cross check it if you have discovered a new species, for example. So that's the beauty of this system, no? Since you converted all your data into a much more compact form, into a numerical form that you can upload in your database, in your catalogs, no? You can use it later on to cross-reference or cross-reference your other discoveries, your other species, no? Sometimes you can create even a much more elaborate system that you only need to measure certain things, and you will create a certain number code for that species. And then once you type that number code in the web, it will generate the identity of your species. That's the cool thing about this. And it's also the same thing with the sequence analysis, or the sequence analysis of your data. You need only to create or sequence your organism, the DNA of the organism. After sequencing the DNA of the organism, you can just copy and paste it in the web, in the internet, and the identity of the organism will come right out. That's how exciting and simple this numerical taxonomy is. Okay? So you can create things like this, and you can upload it in your database. So once you discover the new species, you can just cross-reference it on the range of the length of the forearm and the weight, and you can somehow say that, oh, it's more akin to this species than this species right here. So things like that. That's the beauty of numerical taxonomy. Next, being quantitative is also a plus point for your numerical taxonomy. No? Since it is a quantitative measurement of the different characters of your organism, it provides a much more robust process of discrimination, no, along the spectrum of different character differences out there. So since you are quantitative, you can, since the measurements you're having are quantitative in nature, it can provide a greater discrimination along the different character differences, no, and thus it is much more sensitive in dealing with your data, or discriminating or delimiting the data that you have. No? It's not subjective, so as to speak. And since the more measurements you have, the better you can describe your characters, your taxa too, no? And due to the automotive, I mean the automation that is in Phenetics, you have more time to look into more characters in order to generate more basis for your classification scheme that you're proposing. So the creation of all these empirically derived data variables and data tables, all those encoded data, can help you create a much better description of the characters and a much better description of the species or OTUs that you're describing. But of course, there's also a problem with Phenetics. The first one is that, well, since there are differences in stages in your organism, different life stages and sexual stages in your organism, for example, the different allometry of your organism, you can have a skewed, or it can affect your data points. Say, for example, if for the case of, let's just say you're examining humans, you're measuring human remains, and you are measuring a quite young individual in your population. Of course, a younger individual would have different allometric sizes or different allometry in general than your fully developed organism. It would have different skull size or skull ratio to its body ratio compared to your infant. And of course, it could also have different shoulder measurements, brow ridge, arm length, and so on and so forth. No, it has different ratio due to the different life stages, and also it can create confusion in your data set. If you have a lot of organisms that you have been measuring are old individuals, or a lot of your organisms that you have been measuring are younger individuals, there is a different, of course, it will affect your data, since these 2 points in the life stage of your organism that you're measuring is different in your allometric characters, in your different morphological characters. It will surely affect your data. And that's the thing about human remains, no? Especially for hominid species, we have very few of them. So yeah, the life stages could affect, and also what we call the sexual dimorphism in your organism. It could definitely affect your data points. No, say for example, we all know that organisms have sexual dimorphism, right? That there are difference between your female and your male. And if you, no, for a certain, have been only been measuring the male for that data set, it will skew your data. No, since usually the males are shorter or smaller than your female counterparts and has a quite different tip than your female and also different color tip than your female, it will create different differences in your data points. And also your males have what for Drosophila, it has what we call sex comb right here, but your female does not have that. And for your female, it has different shape on your abdomen or the end of the abdomen. But for your male, for female it is pointed, for male it is blunt. No? So things like that. No, sexual differences among organisms could possibly skew your data, and if you're not paying attention to it, it could really affect the data sets that you're having. So also true for the case of this, no, the peahen and the peacock. No, if you keep on measuring this, the amount or the color, no, the color pattern. We all know that the color pattern of your peacock is much brighter than the male is much brighter than the female, because it uses that to allure or to well entice the female to have sex with him. So things like that, no, sexual dimorphism, and also there could also be a possibility that you are using different similarity coefficients. No? When we say similarity coefficients or coefficients in general, your correlation coefficients, these are, of course, as you have remembered, these are the measures of whether your data sets of the two given groups are similar or they are dissimilar. And when using different similarity coefficient like your Jacquard, Sorensen, Andenberg, and so on and so forth, they have different way of computing for your similarity coefficients. So that's the thing about statistic din eh. You need to have a good idea of what that index of coefficient or coefficient means and how it is computed and what interpretation of that data is. No? So you need to cross-reference all of these similarity coefficients. And different authors uses different similarity coefficients, both in the ecology field, in the zoology field, in the botany field. They use different similarity coefficients because sometimes your data could have a positive correlation on the Jacquard index, but when you compute for its Sorensen dice index, it will have a different coefficient and a negative meaning. Things like that, no? It can really vary from coefficients to coefficients sometimes. So you need to have a grasp of what coefficient should you use and when to use it and how to compute it, of course. So if you have differences in the similarity coefficients that you're using across different references, it could affect your representation or the estimate of the relationship between the OTUs that you're comparing. And the last problem with using numerical taxonomy with phonetics is the possible effects of parallelism and convergence on your classification schemes that you're proposing. No? And if you think about it, Its advantage, the sense that it treats every data points, every numerical measurements, every character attributes that you're measuring as equally weighted. That's also its downfall. No? Its advantage is actually its downfall too, since a system of classification based on the similarity between organisms without regard of their evolutionary relationship is also a blind system. No? When we pertain to or base our observable similarities based on the difference between organism without regard to the assumed genealogy of the organism, we get to be blind, no? And that's the thing here, no? Phonetics always cluster your organisms based on similarity, and it doesn't concern itself with the evolutionary concepts that are present. Phonetics is a mere grouping and clustering of your groups, of your organisms into dissimilar and similar groups. No? It's just a clustering system. So you need to guide it. You need to inform the system of the different evolutionary concept, you as a researcher, so that it is much more, so that you can convert your observation, your classification to a much more evolutionarily correct classification. So, yeah, that's the thing about phonetics, no? Right now, phonetics has been superseded by cladistic for research, especially in the areas of evolutionary relationship among species. But certain methods of phonetics, such as neighbor joining methods, have found their way into the era of phylogenetics because they are a reasonable approximation of the phylogeny of your organism, which are much more easier to do than your Bayesian inference. No, it's much more easier to do and less computationally expensive than your Bayesian inferences. And if you think about it, phonetic relationships or phonetic analysis are unrooted analysis. They do not distinguish between the plesiomorphic characters, the inherited trait from the ancestor, the apomorphic characters, the newly evolved characters. They only concern themselves with the cluster, the groupings of your similar and slightly dissimilar characters. They only look at the differences in the character traits that you have input in the system. No? That's the common problem with phonetic analysis, that sometimes you will have organisms that contain so much plesiomorphic character that it appears to have not changed at all since time immemorial, no? And thus it will create a monophyletic lineage. It will separate that into a monophyletic lineage. But that's not the case. It's still a part of your group. It just so happens that this organism doesn't really change so much in its history. That would be for the case of your organisms that did not change so much, no? Organisms that we call living fossils. Yeah. Also, phonetic analysis can be misled by convergent evolution. No? When your convergent evolution and adaptive radiation happens, it could create problems in your scheme. No? Ito yung napag-usapan natin. We will create what we call phylogenetic pitchfork, in which, in that case, you can't delineate which is which. No? Since you have a convergent evolution, they will all have the same character traits since they are exposed to the same environmental condition. When you measure the character traits, they will have, no, the same size of ears, size of wings, and so on and so forth. And thus, the numerical taxonomy would lump them into one, but they are not into one group. But that's the thing when there's convergent evolution. Also, in adaptive radiation, in the case of adaptive radiation, what will the numerical taxonomy will do is that it will put them into separate monophyletic clades, no? Since they're only basing it on the differences in certain it will put them into monophyletic clades that are different from each other. But that's not the case for adaptive radiation. But when you're using cladistic, it will attempt to solve this problem. So that's your fundamentals of phonetics. I hope you have read the monophyletic, paraphyletic, and polyphyletic readings because it is surely important in this discussion. No? But nevertheless, we all love monophyletic groups, but it seems that we can't always have them. So that's the thing about the grouping systems that we're doing. Okay, so that's it for today. If you have questions, comments, and suggestions, leave it in the comment section below. And if you like the video, please do leave a thumbs up. And once again, this is Sir Patrick signing off. Peace out.